Because each element has its own unique set of energy levels, it also has its own unique set of wavelengths of photons that it can give out. Now, this is going to be a little piece of potassium, and one way you can make it give out all of its characteristic photons is by heating it. So I'm going to heat this piece of potassium, and as you know, it's going to burn with a lovely purple flame. So that's a whole range of photons coming off, but they're all mixed together, and what we see is just purple. We can't see all the different, we can't tell what the different photons are. So we have to pass the purple light. So this is all the different photons together here, and we pass them through a grating, and as you know, a diffraction grating makes the light ray bend, and how much it bends depends on its wavelength. So here we have now the different photons are going to bend different amounts, and so now we get them coming off in different directions. And so if we were to sort of like photograph this bit here, we'd now get the different wavelengths as separate lines, and that's what an emission spectrum is. That's how you get an emission spectrum. Okay, but this is not what you get from stars. This is what you get if you burn something in the lab to force it to give out its characteristic photons. This is not what happens with stars. The centre of a star, where the main nuclear fusion reaction is going on, is giving out all different wavelengths of light on account of its temperature. Now, in the outer layers of the star, you've got gas that isn't doing fusion. So we call it cooler gas. It's not cool, it's thousands of degrees Kelvin, but we call it cooler because it's cooler than the centre. This gas here, these atoms, are not doing fusion. Now, when this light comes out, remember all different wavelengths coming out, only the wavelengths, only the photons that have the right energy to get absorbed by the atoms are absorbed, and all the other photons just sail through. But if you were a photon coming out the centre here, and your energy was exactly the same as one of these energy gaps in one of those atoms, then you would get absorbed. And then when you're re-emitted in some other direction. And so what that means is that the light that continues on to Earth is missing all of those wavelengths. So all those wavelengths that we would see emitted if we heated up that particular atom, we instead find are missing because the atom took them out as the light was passing through. And this is called the absorption spectrum for the star. It's like the negative of the emission spectrum. So where an emission spectrum is black with just those wavelengths on it, the absorption spectrum is a continuous spectrum of light there with black lines where those same wavelengths are missing. By matching the emission spectra of elements from the lab with the lines on the absorption spectra of stars, scientists were able, this is how they worked out what the stars are made of. And so for a bit more practice on emission spectra, here's another question. So the energy of a photon is once again hc over lambda, and so there are our two energies. And now here are the energy levels that we're told produced those two photons. Now this gap here is only 0.92 times 10 to the minus 19 joules. So that one is too small to have produced either of our photons. So this one has to be the larger energy gap, so that's the smaller wavelength. And then this medium-sized gap must be the other one. Okay, and then lastly, we want to know what is the energy, what value goes there, what's the energy of that level. So let's just call it E. And so we know that whatever that energy is, if you take away the energy that is taken away by that photon, you'll get to that. So E, take away the energy of that photon, which was 4.56 times 10 to the minus 19 joules. That will give you that, minus 8.86 times 10 to the minus 19. And that is going to give you minus 4.30 times 10 to the minus 19 joules. So minus 8.86, minus 7.94, and this one is minus 4.30.